this computer. So I started the grading. I've graded about 5 so far, and I will have everything graded by Monday. I finished the other class. The average in the other class was about 80, which is actually pretty good. That's, you know, a great average for a calc exam. And I will post the grades in my math lab as soon as I get them graded, and I'll bring them over to D2L. Typically, I put them in my math lab first, and then once I get everything sorted out, I import them over to D2L. So they'll be there certainly by Monday. But if you're trying to look ahead of time, I would, just so you know, I would post them in my math lab first. My math lab does a nice job of averaging and doing all the data that I want done on them. Okay, so at any rate, let's go ahead and start with our chapter 8. So this, if we look, chapter 8 is all about integration. So we're going to learn a whole bunch of new integration techniques. We're going to look at some random integration techniques first. And then we're going to get into our second formal technique of integration. Right now, you all know how to integrate using trigonometric substitution. What am I saying? I just got distracted. You all know how to integrate with substitution, U-substitution. We will get to trigonometric substitution, but at this point, you just know U-sub. So integration by parts will be sort of your second formal integration technique. And in 8.1, we're just going to do a bunch of random things. And then trigonometric integrals, and then we're going to do trigonometric substitution, and then we're going to do PFD, and then we're going to do some improper integration. So chapter 8 is a long chapter. The next exam is chapter 8 and chapter 9. Chapter 9 just has two sections on differential equations, kind of an overview of differential equations. And the way we solve a differential equation is essentially with integration. So these sections are pretty straightforward. Kind of nice, similar to how we finished the first unit with just 2 sections or 1 section in chapter 7. Same idea here. We'll do 2 sections in chapter 9, and they tend to be easier than the other stuff in chapter 8. So we kind of finish in a way that's not too overwhelming. Okay, so here is an integration table, and you can find this in your book, in your ebook, wherever online. These integration tables are everywhere. These are sort of the most common ones that we're going to see in this class. And many of them you should already know. You should already know how to do the exponential with the reverse chain rule. You should know how to do your trigonometric ones so far. There's the power rule. There's the log. These 3 you should have seen in Calc 1, but you probably only did them with a table, I would imagine. The most important of these inverse ones will be the arctangent one. That's the one you'll see the most, and we'll talk about why that is and why it shows up so frequently as we move through this content. But these 3 super important. The arcsecant one we'll use less frequently. Use the arctan the most, arcsine the next most. So these 2 I would definitely start paying more and more attention to. And then we're going to talk about these 4 integrals of trig functions. And what I want you to notice is that when we're not talking about sine or cosine, so these other 4, notice that they all integrate to log functions. So if you're not dealing with a sine or a cosine, you are going to integrate to a log. The antiderivative will be a log. And we'll figure out why that is and how to put them in log form, because you already know log form. You already know that if something is going to integrate to a log, you have to have some sort of, there's some sort of manipulation on the integral that will allow you to put it in log form. So the denominator's derivative will be the numerator. And we'll talk about how that is. When you're looking at them right here, you're probably thinking, how the heck do I put secant in log form? That seems pretty odd. So we'll get to that soon. Okay, so let's take a formal look at power reduction. We have talked about it informally. We saw that there was an example on the first homework that did need power reduction, even though they hadn't really talked about power reduction in the book yet. But that's okay, not a problem. So let's go ahead and notice that these power reduction identities do exactly that. They're reducing the power. So when we look at the trig function on the left here, the power is 2, and on the right, the trig function has a power of 1, and same over here. So that's why we call them power reduction. When we reduce the power, we are creating an integrable function. Let's see. So let's take a look at this first one here. So we're going to replace this, and you can do this in lots of ways. You can rewrite the identity as 2 separate terms. This is how I write it quite frequently. You could write it as a 1/2 being factored out to the front. I tend to write it this way because in the long run, we are going to have a constant of integration, which is going to give us 3 terms. And having this 1/2 just factored to the front of the first 2 terms, it isn't that helpful. So I'm going to integrate here with respect to theta. Stop me if you're stuck on anything. Integral of cosine 2 theta, the integral of the cosine function is sine. So we're going to have sine of the same angle. But then what do we need to do? There's something we have to do. Just so I know that you're out there and I'm not just talking to a screen, somebody tell me, what is the next step? What's going to go on in here?
Change the sign.
Oh, we will have to, the sign is still going to stay negative though, because the integral of cosine is sine. So this minus is going to drop. Something's going to happen because of this though. What do you think is going to happen?
Oh, RCR.
RCR, exactly. So we're going to have to divide by that too, because this is linear. That tells us that we have to do an RCR at the end. So we're going to divide by 2, which is going to make this coefficient 1/4 instead of just 1/2. And then we have our constant of integration. And that's it. So that is how we are going to integrate sine squared. We have to power reduce it. And then we have to integrate term by term. And that's right, divide by 2. All right, let's take a peek at this one. So this one also has to be power reduced. So we're going to write this as the integral. We're going to look above, and it's 1/2 plus 1/2 if I distribute that 2 into the numerator. Cosine. All right, what angle do you think? Cosine of what angle?
3 theta.
Nope.
6 theta.
6 theta. So look up here in the identity, we see that there's a 2 here. So whatever the angle is on the left, on the right, it's going to end up being doubled. So that's the pattern. When we look at that identity, on the left, we have a single angle, and on the right, we are going to double it. So right here, we have a single angle, and then that's going to be doubled. Does that make sense to everyone?
Yep, that makes sense.
Okay, good. Good. So it's kind of the it's what you pay for power reducing. If you power reduce, you double the angle. That's going to be kind of this pattern that we see with these. So now we've doubled the angle, and now we can integrate. And so this will again be 1/2 theta. And here, integral of cosine is still just sine, same angle. And now we're going to have to divide by
6.
6. Yeah. So we're going to end up with 1/12 here. So same idea. We have to use an RCR there. Because this is linear, we have to remember to do an RCR. All right. So those are 2 identities that you'll definitely want to have memorized, because we're going to see those quite a bit.
So we should memorize the power reduction, right? The 2 sine, or yeah, basically the answer of 2 sine and cosine, right?
So you're going to want to memorize these 2 identities right here, that sine squared is 1/2 minus 1/2 cosine 2 theta, and cosine squared is 1/2 plus 1/2 cosine of 2 theta. So
Okay.
those 2 identities right there. There are other reduction identities, but these are the only 2 that we ever memorize, just for sine squared and cosine squared. Uh-oh, what's it doing? Don't be weird. It's being weird on me. It changed all my color. Why did it do that? So let me just do, I want to switch that. Not sure why. Sometimes with this pen, it does this thing where it just doesn't want to release the ink, and the ink is just sort of floating on the page, and I don't quite know why. Oh, it's not wanting to change that either. Let's try one more time. All right. So let's move on to substitution. So I'm going to do this problem twice. We're going to do it once with substitution, and then we're going to do it once with RCR, just as kind of reinforcement that you can do either. But my strategy with you all is to really encourage you to use RCR, because that is a much faster, more efficient way to go. And we have a linear substitution, 75% of the time we use substitution, it's linear. So getting RCR down is just a very good thing to do. But if we weren't going to do RCR, if we were going to do substitution, then we go through this process. So we're going to let u be the exponent, and then we're going to take the differential of both sides. And then up here, we're going to rewrite this as e to the u. And now we want to replace this dx. So to replace that dx, we are going to have to isolate dx. So we're going to divide both sides by -4. And there, now we have an expression for dx. And so du over -4 is going to go in here. And usually we put that constant right out in front. We're dividing by -4, so that means multiplying by -1/4. And we know how to integrate an exponential. The integral, or the derivative of an exponential, is itself. Now, we need to get back to the original variable, which is an x. So we're going to do that. We call this back substitution. So we're going to sub back in for the u and go back to x. So there is our antiderivative. And if we did it with RCR, let's notice how much faster it is. We would say the integral of an exponential is itself. But then because we have this linear exponent, we're going to use RCR. So we're going to divide by the derivative of the exponent. And we're done. That's it. So doing RCR is a massive time saver. We saved 1, 2, 3, 4, 5 steps.
Would we be able to see like for other problems going forward in this lesson, could you still do the RCR?
Oh
So
yeah,
that way we can get used to it.
We're going to do it 2 more times right here. Absolutely. So look right here. This is linear. So RCR. This is also linear. So we'll do RCR here also. So anytime we have a substitution with that would be linear, we can always go to RCR. All right. So
Can you tell me? I have a
say that
question.
again.
So can you tell me how did you get that -1/4 using
Here?
RCR? Yeah.
So what is the derivative of this exponent? So if we have 3 minus 4x, what's the derivative of that?
-4.
Yep. And so RCR says that you divide by whatever that derivative is.
Oh, okay. Yeah.
So that's what this is right here. This is division by -4. Does that make sense?
Yes.
All right, good. And so down here, when we integrate this cosine function, the integral of cosine is sine of the same angle. And what is the derivative of that angle? Derivative is
5.
5. So we're going to divide by 5. So that will be our antiderivative. Now we're going to come over to this one. And first, let's go ahead and just rewrite this so that we have a 1/2 power. Sometimes it's a little more obvious that you're going to use the power rule when you have the power form instead of the radical form. You don't have to, of course. So then we just go through our regular process. Now this is only working because this is a linear substitution. When it's a linear substitution, you can just do it. You can just integrate with the power rule as if you normally would. So this is going to be 3/2. We add 1. And when we add 1, we get the 3/2. When we divide by 3/2, that's the same as multiplying by 2/3. And then what is the RCR part? Divide by
4.
4. So if we simplify, we'll have 1/6 4x minus 1 to the 3/2 plus c. All right, stare at that for a moment and let me know if there's any piece of that that's not totally clear.
I have a question. So does it matter which one you do first? Do you have to do the outside first, then the inside, or does it always have to be, or could you do the inside first, then the outside?
So we're always going to do the outside first. So here the outside function is cosine. So the first thing we did was integrate cosine. And then at the very end, we looked at the inside function and did the derivative, the division by the derivative of the inside. So definitely start with the outside. So here, the outside function is the square root. And so we did this first. We used the power rule to integrate that outside function.
Okay, that makes sense.
And then at the end, the last step was to go to the inside and take the derivative and divide by that derivative to get the 4 in the denominator. Okie dokie. RCR. I cannot believe we're doing Zoom again.
I kind of don't mind just because it's also kind of nice to just not drive, but also, yeah, I totally understand where you're coming from.
Yeah, I can't believe that you guys get nailed twice in in like 1 month. Okay. I mean, at least better than not meeting at all and saying, hey, just read the book and I'll catch up with you on Monday. That would be brutal. Okay, so the book calls this next thing, I know in March is not even here yet. What's going to happen when we get more than 4 inches of snow? 10 years ago, we never canceled class unless we had like a foot minimum. Now all these Colorado immigrants are afraid of 4 inches of snow. All right, so let's take a look at this one. The book calls this subtle substitution, and it's kind of a misnomer. It seems a little misleading. Really, our strategy is to eliminate the negative exponent or to clear the negative exponent. This is what I would, if I was asked to name this, I would say, let's call it the clearing of negative exponents technique. So we see that one negative exponent right there. That's kind of annoying, and it makes things more complicated than it needs to be. And so in math, frequently we use this technique where we multiply by 1. And multiplying by 1 is the technique that's going to work here. And so what we want to do is multiply the numerator and the denominator by something that is going to clear out that negative exponent. And so here's what we do. So we are going to multiply numerator and denominator by something that's going to clear out that negative exponent. And it will turn out, and hopefully you already know this, that is going to be what we multiply by. Because we know already that e to the minus z times e to the z is e to the 0 which is 1. So if we multiply an exponential with a negative exponent by the exact same exponential, but with the positive version of the exponent, it's going to clear out the negative. So let's go ahead and do that. And let's see how that works. So in the numerator, we have e to the 2z times e to the 1z. We add the exponents and get 3z. In the denominator, we have to distribute. Right, this e to the z needs to be shared. It's going to go to that term and it's going to go to that term. It has to be distributed. So it's going to be e to the 2z times e to the z, which is e to the 3z, minus 4.
I have a question.
Yeah.
So can't we take that negative e to the negative z to the numerator?
No, we can't take it to the numerator directly because of this minus. Right, so when you have a denominator that has 2 terms, let's just suppose we had this, this can't pop up to the top because of this, because of the plus here. Let me ask you a quick, can you see my mouse moving over the plus sign right now?
Yes.
Okay, good. So does that make sense? Whereas
Yep.
if we just had this, then yeah, then you could just move it straight up. Okay, so go ahead.
What if we have multiplication sign over there?
Yeah, multiplication, then we can just move it up. Yep.
Oh, that makes sense.
Absolutely. Absolutely. And now we are, our strategy is kind of what you just alluded to. We are bumping the exponent up in the numerator. But it's not done by moving it up because this is not multiplication. So we have to multiply top and bottom by e to the z. And then when we distribute, that e to the minus z is essentially gone. And it's kind of like we moved it up to the top, but we also have to make sure that we're moving this exponent up also.
Will there be cases where when you do try to get rid of the negative exponent where it won't, let's just say like the E3Z won't add with whatever you're multiplying?
Yeah, so you're saying that when we multiply top and bottom by whatever it is to clear this, that these won't be like. And for our purposes, they will be like. You're not going to end up with like an e to the 2z and then something that you can't combine it with.
Okay.
Like down here, we have to multiply up and down by y to the 3. So it would not be cool if there was an e to the y up here, because then if you multiply by y cubed, you can't combine them. So we won't see that. So we will be able to combine them. All right, so now when we look at this, this is almost in what form?
U sub.
Log form?
We could definitely use u sub, but more precisely, it's almost in log form, right?
Yep.
What is the derivative of e to the 3z minus 4?
E to the 3z. Oh, 3e, yeah.
E to the 3z times 3. And that's almost the numerator, right?
Mm-hmm.
So what we're going to do is this same strategy where we can just multiply by 1. If we put a 3 right there, and then we balance it by putting a 3 in the denominator, we just multiply by 1, and multiplying by 1 is totally fine. Now it's in log form. So this is in log form. Remember, log form is when the denominator has a derivative that is exactly the numerator. And once it's in logarithmic form, we know that the integral will be natural log of the absolute value of the denominator. So multiplying by 1 is a very, very common strategy when you're integrating. lots of times when you're integrating, you want to just sort of massage the integrand a little bit, and usually massaging is done by multiplying by 1. All right, so let's take a look at this next one. Again, we want to multiply by 1. And if we multiply numerator and denominator by the largest power, so the biggest negative number, if you will, if we just counteract that, we'll take care of all the other powers that are also negative that have a magnitude in the exponent that's less than the 3. So the magnitude of this exponent's 1, and it will be taken care of automatically. So let's see how that is.
Hey, Jim, I had a question.
Absolutely.
What if there's multiple, like an X and a Y, and they both have negative exponents? Do you multiply by
Great.
the X and,
Yeah, I hear you. So one thing that we do in Calc 2 thus far is we're only dealing with one variable. So there's no way that we're going to have a commingling of X's and Y's. So our integrands are always going to be single variables. And that will change when you get into Calc 3, where you deal with multivariable functions. Then you could have X's and Y's, or X's and Y's and Z's. So let me just say that if you did have 2 letters in there, an X and a Y, that's usually done with a double integral and not just a single integral. And when you
Okay.
have 3 variables in there, you're going to end up with a triple integral instead of a single integral. So we are not going to be, we'll never see X's and Y's in a single integral.
Yeah, that's more Calc 3 stuff then.
Yeah, that's in Calc 3, exactly.
Okay, cool, thanks.
Yep, absolutely. So when you're doing a double integral is going to be another way to find, you can find volume with a double integral. Just like we find area with a single integral. A single integral gives you the area beneath a curve. A double integral will give you the area beneath us. It's going to give you the area beneath a surface. So it's going to give you a volume. And a triple integral is going to do something a little more complicated. It can find volume, but it can also find density. You can also integrate density to get mass if you have a solid object. Okay, so for us, we're just going to see the one letter in here. It's the only thing is the Y. And if we multiply numerator and denominator by that Y cubed, this is what we end up with. So let's just make sure everyone gets that. So we're distributing this Y cubed. This Y cubed is being shared. It's being multiplied by each term in the denominator. And does everybody see why you get what you get?
Is it because you're splitting the integral in 2?
We're not going to split the integral in 2, but we're going to distribute. So we're multiplying this Y cubed by both this and this. We're distributing it. But we can't split the integral. You can't split an integral based on the denominator. We are going to talk about splitting integrals real soon, but we can't split an integral with the denominator. If the numerator had 2 terms and the denominator had 1, then yes, then you could split it. You could split it like that. But when the denominator is 2 terms, there's no way for you to split it apart. Where's my keyboard? Yeah, so we can't do a split, unfortunately. All right. So what we hope is that when we do this multiplication to clear out the negative exponents, what we're hoping is that that was the main strategy, and now we can just integrate like we did up here. We had a little bit of manipulation to put it in log form, but we could integrate right away. Well, unfortunately, this one is going to put us into another one of these one-off situations. And the one-off situation that this is in is as follows. Let's go back to grade school for a minute. And let's remember that if we had something like 14 divided by 3, and your teacher said, write that as a mixed number, most of you pretty quickly would say, oh, well, that's 4 2/3. Is everybody comfortable with that? Everyone remember, we divide the 3 into 14, and the first thing we get is the quotient. That's the 4 up there is the quotient, and then we subtract. And then once this number is less than that number, you know, this is the remainder, and it goes over the divisor. Over that number is the divisor. So there's a similar thing happening with rational functions. This integrand has a rational function in it. And this rational function, even though you don't hear the word improper tossed around with rational functions, when you look at those exponents, the numerator has a higher exponent than the denominator. And so that is improper. That's improper in the same context that over here, the 14 is bigger than the 3. So that's not really a fraction, if you will. Right? When someone says a fraction, usually you think part of a whole. So when someone says a fraction, you're usually thinking less than a whole. It's a half or a third or a fourth or, you know, 4/5. When we write an improper fraction, it's called improper because you're not really dealing with a fraction of something anymore. You actually have more than a whole. Like 14/3, okay, it's written as a fraction, but it's actually 4 2/3. So this is referred to as a fraction, but it's an improper fraction. It's not sort of like, it's not a fraction in the kind of the intuitive sense of the word fraction. All right, so same idea over here. This is improper. I'm going to call it improper. Most books don't really identify this as something that they wouldn't call this an improper rational function, but I'm going to use that word. Some books do, some books don't. And the question is, okay, what the heck do we do? Well, we do the same thing we just did over here. This symbol here means divide. So let's divide. And so anytime we have an improper rational expression inside the integrand, we are going to have to do long division. So today we're going to do a lot of algebra, a lot of college algebra. So y squared plus 1 divided into y cubed. So then we put up here in the top, we say, okay, what multiplied by y squared gives us y cubed? And then we distribute it to each of these terms. So this is going to give us y cubed plus y. And then we have to subtract. And if it's helpful to you, you can put a placeholder up here. You can just say that that's 0y. And then when we go ahead and do the subtraction, we're going to end up with negative y. So we're subtracting. So we're going to do y cubed minus y cubed, which is 0. And then we're going to do 0y minus positive y. And 0 minus positive is negative. Okay, that erase. All right. Something fishy's happening again. I got to figure out how to stop it from being fishy. All right. Any questions on that?
Sorry, where did the y cubed plus y come from?
So
you're
that,
subtracting?
So that's coming from distributing the, grab green. So we're taking this and we're distributing it. We're multiplying it by that and getting the y cubed. And then we multiply it by the 1 and get the y. Does that make sense?
Kind of, yeah. Can you just remind me where the y at the top came from?
Where the y at the top came from?
Yep.
Yes. So we're looking inside here at this y cubed right in here. And we're looking out here at the y squared, and we're putting up here whatever needs to be put here so that when you multiply by that, you match this.
Okay.
So we
Okay,
want to
cool.
match the y cubed, so we multiply by y.
Okay.
I have
then
another.
Yeah, go for it.
So how does it ended up getting negative y over there?
So we subtract. So this is the minus, and we have this quantity y cubed plus y. and we're subtracting it. So it's y cubed minus y cubed, which is 0y cubed. And up here we have a placeholder of 0y. So 0 minus 1 is negative 1y.
Oh, okay.
And then as soon as this expression here has a lower power, then we're done. So as soon as that's lower, just like over here, my eraser took out some of this, so we subtracted and got 2. So just like over here, when this is less than that, we're done, and this is the remainder. So over here, the negative y is the remainder. And then we're going to do the same thing that we did with back this grade school math. We're going to take the quotient. So this right here is called the quotient. This is called the remainder. And that remainder is going to be put over the divisor, which is also the denominator. Same thing. So we have y quotient minus the remainder put over the divisor. And now we can integrate. This is okay now because this is proper. And as long as it's proper, there's going to be a technique, unless we have some really nasty thing. If it's proper, we should be able to integrate it. Okay, let's see. Yeah, not quite sure why the pen just wants to change color every once in a while. All right, so now we can integrate. So the integral of y is y squared over 2. And what form is this second part almost in?
It's almost in log form.
Yeah, it's almost in log form. Let me just rewrite it down here to make sure that everybody's seeing that. So what we can do here is separate this into 2 integrals, right? We can just, the integral symbol can be distributed just like a derivative. And then the y squared over 2, no problem. This is almost log form, and to put it in log form, we'll just do that. So the numerator has to be the derivative of the denominator. And if we multiply the numerator by 2, we have to multiply the denominator by 2 to offset it. So now it's in log form. I did it again. It just changed that. Someday I'll figure out why it changes, I hope. So now we're going to have plus, or actually minus, 1/2 natural log absolute value y squared plus 1 plus c. All right, any piece of that you're not 100% sure about?
I have a question.
Yeah,
If the remainder was positive, would it be plus y over y squared plus 1?
yep, that's exactly right. So whatever this sign is over there, that is going to dictate. So right there on the remainder, if you had a minus, this will be a minus. And if that happened to be a plus, then you'd have a plus there. That's right.
Okay, so I'm still a little bit confused. So I see where you did the where you multiply it by 3 and you got 3 on the top and then 2 y squared plus 1 at the bottom.
Mhm.
And then you started to do
Long division.
long division. And then from there, that's where I got lost because I know how you got the negative y, but then you got integral of y minus y over y squared plus 1.
Mhm.
How'd you get that?
So it's very similar to over here. Let's look at the number again. So over here, 4 2/3 is 4 plus 2/3. So it's that same idea. This is the quotient right here. And then we have the remainder divided by the divisor. There's the remainder. There's the divisor. So it's that same idea. The remainder is right here, and that gets put in the numerator, and the divisor is over here, and that gets put in the denominator.
Okay, that makes sense.
All right, let's do another one. Let's do another long division because, yeah, because that's what we need to do. So let's look at the example down here first, because that's where that's going to be another division. So let's do that. Okay, so the first thing here, I'm going to rewrite this so that it's in descending order in the numerator also. So let's just rewrite this. It's a little easier to divide polynomials when the functions are written in descending order. So this is improper. So we're going to divide the denominator into the numerator. And I'm going to leave a little space here because I suspect there's going to be an x squared in here somewhere because of that. So let's go ahead and go from there. So the first step is to try to match this negative x to the fourth. So we want to put something up here that when multiplied by x squared gives us negative x to the fourth.
Negative x squared.
Yeah, we're going to put in negative x squared because negative x squared times x squared is negative x to the fourth. Now that negative x squared, it's got to be multiplied by this whole polynomial over here. So then we're going to have minus 4x squared. And we are going to subtract that whole quantity from what's above it. So this will be negative x to the fourth minus a minus is plus x to the fourth. That's 0. And then we have 0 minus 4, which is plus 4 x squared. And then we drop the plus 6. This thing just comes down when we need it. So now we're back up on top again, and we say to ourselves, what multiplied by x squared is going to give us 4x squared?
It'll be 4.
So now we distribute. We take that 4 and we're distributing it across this. 4 times x squared is 4x squared. 4 times 4 is 16. And now we have to subtract. So 4x squared minus 4x squared is 0. And then how about the constant? What constant should we have there?
Negative 10.
Negative 10. This is the remainder. So negative 10 is the remainder. So we put over here the quotient, then the remainder over the divisor. So it's quotient plus remainder over divisor. There's the remainder, there's the quotient, and that's the divisor.
Jim, wouldn't it be plus because it's a negative over a negative?
So we have to remember that this is 6 minus positive 16.
I mean, at the bottom,
Here?
the remainder is negative 10. And
Yep.
isn't it negative 10 over negative x squared? Oh, it's that whole expression.
Yes.
Are you missing a minus sign then in the denominator?
No. Because this is the divisor. That has no minus in it. And that's what's down here. Let's go back and look at the other one.
Oh, no. Never mind. Sorry. I know what you're saying.
All right, got it. Yeah,
Yeah,
so
yeah.
here, this remainder was negative, and so that's what that negative is here. You can think of this as, if you wanted to, you can think of this as plus and put the minus up there. But we would usually drag it out to the front.
Okay, so I get the process, but how does he get that 0x squared while doing long division?
Right here,
Yeah.
It's just a placeholder. So you don't have to put that in, but when we do the negative x squared times 4, we have negative 4x squared, and usually it's a little easier to see that there's 0x squared up here. You know, what we try to do is line up the powers so that everything matches. It gets very awkward if you had negative x to the 4th plus 6 and you have negative 4x squared under the 6. So usually what we do is try to create columns so that we can have all the powers of 4, all the powers of 2, all the constants lined up.
So how are we gonna know what kind of placeholder we need to use?
We don't. We just have to start multiplying. So as soon as we multiply this x squared here by 4, we know we need a placeholder for x squared.
Oh,
Yeah, so we don't know ahead of time though. It really is kind of, we just sort of discover it as we go.
get it.
Yeah, it's not necessarily obvious.
Tim,
Yes.
is there ever gonna be like where we're dividing or what we're dividing by is negative and then the remainder and the divisor would make it a positive?
Yeah, definitely. Yeah, it's definitely possible. So we could have a negative right out here in front. Yeah, that's certainly possible. Yeah, could get, this is usually about as hard as it will get though. It's not going to get super, you can have some pretty messy long division with fractions and things, but we're going to keep it pretty, we'll keep it mostly with integers. All right, so let's go ahead and integrate here. And let's integrate the first part. The first 2 terms are simple enough. This is the power rule. And then over here, I'm going to distribute, or I'm going to factor out the 10. And let me just rewrite this integral once I factored out the 10. All right, so we're sitting there right now. And this is an arctangent. This is going to be our most common one. And I want to show you something. So the arctangent integral looks like that. That's our basic one. And we look here and we see that, oh gosh, there's a 4, there's not a 1. And if we jump back to the integration table here for arctan, we see that they put this 1 over a in front. And if you look at the inverse sine one, there's no 1 over a in front. And if you look at the inverse secant, there is a 1 over a in front. So we have this dilemma that if this is not a 1, we need to either put a 1 over 2 in front or not a 1 over 2. And inside the arctan, you put an x over a, so an x over 2, and it gets a little tedious to remember that detail. So what I'm going to show us is a way that we do not have to remember that detail. So as long as you remember your basic integration formula for arctan, and you know how to do reverse chain rule, that's all we need to know. We don't need to also remember what to do if this is not a 1. So this is going to be a strategy that I think is very helpful because we only have to remember our 3 basic inverse trig integrals. We don't have to remember if this is not a 1. And when we get to a topic called trigonometric substitution, if you get efficient at using this with a 1, it will be a lot easier. So let's try it. So here's what I'm saying. I'm saying we want to have a sum of squares in the denominator with a 1. So right now we have a sum of squares without a 1. So to get this term right here to be a 1, we're going to factor it out to the front. All right, we're going to factor it out. But if you factor it out, there is no 4 right here in the x squared. So there's no 4 to be pulled out. So what it does is introduce a 4 into the denominator of that term. If you were to distribute this 4 back, right, it would cancel with that, giving you back to x squared. and it would multiply by the 1, giving you back to 4. So hopefully that makes perfect sense to you. If it doesn't make perfect sense, we can also do this. We could say to ourselves, well, there's no 4 here to factor, so I'm going to put 1 in because we're creative math people. We just put in what we need. But we know that we're only creative to a certain extent. We have to balance our creativity. So we want a 4, so we put a 4. But then reality strikes, and if you multiply by 4, you also have to divide by 4 to keep the balance, to keep the harmony. And so we're multiplying by 1 again. And now this 4 is common, so it can factor to the front. And what's left is the x squared over 4. And then we're going to do one more thing so that we can implement RCR. So this will simplify. And then over here, and there's a dx there. And over here, we're going to have x divided by 2 quantity squared plus 1. And that's an important thing. We want to have the denominator written as a sum of squares with 1. Now we have the denominator written as a sum of squares with 1.
Does that say 1 plus x squared or hx squared?
Let's see, whereabouts?
The red.
That's an x.
Okay.
That x,
And
that thing
that's
right
a
there?
1 plus.
Yes. 1 plus x squared. And now we can integrate this with our basic trig integral in conjunction with RCR. So this will be negative x cubed over 3 plus 4x minus 5 halves. We now are in arctan form. When you have 1 divided by a sum of squares with 1, that's arctan. And I'm going to leave a little space for RCR. So then this will be arctangent of x over 2. And what is the derivative of x over 2?
One half.
1/2. So remember with RCR, as long as what's inside is linear, and this is linear, so this is RCR, we divide by that derivative. So we're going to divide by 1/2, which means multiply by 2. And then we have our constant of integration as well. So there is our answer. We could cancel out this 2 here. Those will cancel. And that's our
Hey, Jim.
antiderivative.
I
Yeah,
had a question. So
for it.
like in most math classes before this, we basically had cookie cutter stuff to do, you know, like we just followed steps.
Yeah.
And now it's kind of more creative problem solving and manipulating things and stuff. Is there like multiple ways to do a problem basically? Or will it usually have kind of one thing you're looking for?
It is, that's a really good question. And so when we look at this section is a hodgepodge of slightly one-off strategies at work. And for the most part, there's not a lot of variation. So like with this one, we have to do long division. With this one up here, we're going to do something called fraction splitting. So in this section, it's a sort of a hodgepodge of different one-off techniques and not quite so procedure-based like you're referring to. But as soon as we get to the next sections, when we get to integration by parts, this is going to be very procedural based. So all these techniques that we're going to learn down here, we will have step 1, step 2, step 3, step 4. But these one-off ones are much more, like you said, creative problem solving. They're not going to lend themselves to kind of that systematic approach that we are going to have in the subsequent sections. But luckily, these one-offs, there's only like 4 of them. And hopefully that won't be too many. It can feel, integration in general can feel very random because there aren't rules. Like with derivatives, there's always a freaking rule. If it's a product, use the product rule. If it's a quotient, use the quotient rule. If it's a power, use the power rule. With integration, it's just not that simple, unfortunately. All right, let's take a peek at this one up here, because this one is another one that we are going to see a lot. This improper fraction thing is definitely, I would put it in the one-off category. Fraction splitting, we are going to see a lot. This is going to come up a ton. So let's think about fraction splitting. And I forget, somebody asked something earlier about the denominator being able to separate the denominator. And one thing we cannot do is separate a denominator when it's two terms, like we can't break it apart. It's two terms, which is in general one of our problems. And here, what we noticed is that this denominator is actually just one term, and the numerator is two terms. And in this scenario, it's great. If the denominator is one term, you can then do this kind of thing, where we are going to break it into two terms, and we're just going to separate it into a pair of integrals, and that denominator is going to be distributed like this. And so this strategy comes up a lot, where the denominator is, one term, the numerator is two, and then you share the denominator, you distribute it. Now, when we look at this setup here, the second integral is an arc sine. And this arc sine, we've got the formula right there. We could go through the factoring out the four thing like I did below, but I don't want to focus on that part of it. So let's just use the formula for this one. But this first integral, what technique can we use for that integral? And you don't have a lot of techniques before today.
Long division?
Well, we're not going to use long division because this is not an improper fraction. The long division is always going to be when we have a polynomial over a polynomial. And we don't have that situation up there because this is a square root. So
U sub.
Yeah, U sub, exactly. U sub is what we're going to use. So that is the one technique of integration that you have sort of prior today. That's your only formal technique. And so what we're going to do, let's just do it off to the side, is let u be what's inside the square root. So then du will be minus 2x dx. And when I look in this numerator, I see an x dx right there. And so we're going to isolate the x dx over here. And that will allow us to do u sub. So let's take a peek at what that u sub is going to look like. So we're going to have we're going to have 3. The 3 can come out to the front. And then x dx is du over negative 2. So I'm going to write that as du, and the over negative 2, I'll put the over negative 2 out in front because that's a constant. And then the square root part, we have the square root of u, and that's in the denominator. So if we pop it to the numerator, that will be u to the negative 1/2. So take a look at that sub and let me know if there's anything there you're not sure about. And then we're going to go ahead and just use the integration table for this one. This is going to be x over 2. And there's no 1 over a out in front for sine, inverse sine. Okay, so how about the integration of this? Well, that's just a power rule. So we have a technique for that already. I'm going to leave a little space. This is going to be u to the positive 1/2 divided by positive 1/2 means multiply by 2. Inverse sine of x halves plus c. And then one more step. Oh, is that going to let me split that? And then our final step is to do our back substitution. So we're gonna have -3 square root 4 minus x squared plus inverse sine of x over 2. All right, any questions on those steps? Well,
I
go
just need
with-
to, I just need to remember I just need to remember the arc sign or. Yep, that one, that formula right there.
yeah, exactly. So we'll see the arc sine one and the arc tangent one a lot. But the one that I want you to remember, I don't want you to necessarily remember the general one, but the more specific one when we just have 1 minus x squared. So if this is the one that you should memorize, just this one. Because we'll avoid the a by doing the factorization like we did below a inverse tangent. But that part you should know. All right, let's go ahead. It's 4 o'clock. So why don't we go ahead? It's 4:03 according to my thing. So let's go ahead and take a break, take a 10-minute break and look over what we've done so far. I'm going to run, grab a drink, go to the bathroom, come back. And if anyone has a question during this 10 minutes, I'll be back and I can answer those questions. Make sure that you are following everything that we've done so far. And I will see you back in 10 minutes. Or less, I guess, for me. You don't have to be back for 10. All right, so our next technique, again, we get to dive back into our college algebra techniques. Completing the square, another technique that you all know and love. So here goes. Here's how we're going to complete the square here. We look in this denominator and we cannot factor that. So here's what we're going to do. We want to complete the square using the first two terms. And we know that to complete the square, we take the coefficient of x, divide it by 2, and then square it. So 4 divided by 2 is 2, 2 squared is 4. So we know we need a 4 right here. We need a 4 right there. Then we will have a perfect square trinomial, and that's factorable. So there are two ways to do this. One way is to put a +4 and a -4. So you're essentially adding 0. And the other way is just to notice that we have an 8 right there. We could just borrow 4 from it. So if we turn the 8 into a 4 + 4, then we have a perfect square trinomial. And that perfect square trinomial will factor into x + 2 quantity squared. Then we have the +4. So we have that. Now we have a couple of things that we could do. The most natural thing, I think, would be to get rid of that x + 2. And if we look up at this arctangent business, we have a sum of squares here. And it'd be super convenient if this was just a u instead of an x + 2. That'll make our lives a little bit easier. So let's go ahead and do that. Let's just let u be x + 2, so then du is dx. So we're just going to make that substitution. All right. So In the denominator, we're going to have u squared plus 4. The dx turns into a du, but what about the numerator? The numerator has an x in it. We can't have x's and u's in the same integrand, so how do we convert this x? How do we turn that into something over here that's just u's?
Could you manipulate that u sub to have u over 2 equals x?
100%. Great. So we come up here, we can manipulate this and rewrite it like that. So that let statement allows us to go back and forth between u's and x's. We can exchange an x for a u or exchange a u for an x. We can do whatever that statement allows us to do. So that becomes a u minus 2. And then we have to convert our limits of integration. So this is an x limit right here. So if we plug it in up there, we'll get a u limit of 2. That's an x limit. If we plug it in up there, we'll get a u equals 4. All right, so that's all good. And now what we're going to do is split the fraction. So we saw this on the last slide. We can, if we have a numerator that has 2 terms, let's not make that so big, we can split the fraction. So I'm going to take this u squared plus 4, and I'm going to divide it into each part of the numerator. And when I put it into the second part, I'll factor out the -2. And this is going to go from 2 to 4 also. So what form is this first integral almost in?
Log.
Arctangent.
Log form. So that first one is, now it's in log form when we multiply by 2 and divide by 2. The derivative of u squared plus 4 is 2u, so that's log form. And this one is an arctan. And again, we could factor this 4 out and we could use our basic arctan integral along with RCR, but let's just use this for now because we'll get into that factoring of the 4 out. We'll be doing a lot of that in a little bit. So let's just roll with this. So this will be 1/2 natural log absolute value u squared plus 4 from 2 to 4. And we could just put the 2 to 4 on the whole thing, because when we integrate here, we're going to get an arctangent thing also from 2 to 4. So we can just do it overall. So that's -2. And then if we look up here, arctan has a 1 over a out in front. So that's a 1/2. A is squared here. So this is a 2 squared. So a is 2. And then it's arctangent of x divided by a. So in this case, u over 2. And it's not a plus c because we have a definite integral from 2 to 4. These cancel. Let's plug and chug here. So plugging in the 4, we're going to get 1/2 natural log 16 plus 4 is 20 minus arctangent of 2. And then we subtract off antiderivative at 2. So we'll have that. We're subtracting off, so subtracting a minus makes a plus. Arctangent of 1. We can do a little simplification here. Notice that we have a log minus a log. A log minus a log turns into a division. So this is going to be 1/2 natural log of 20 over 8. 4 goes into 25 times 4 goes into 8 twice. Minus arctangent of 2 plus, what is arctangent of 1? Pi over 4. Arctangent of 2 is not a special angle, so that can't be simplified.
I had a few questions. So I see how you got the 4 + 4 because you basically broke up the 8.
Mhm.
And then you basically pulled out a 4 out of the whole bottom problem. Is that correct? On the
Um,
next term?
here,
Yeah, you pulled a 4 out of everything.
no, I didn't pull a 4 out. I factored that this polynomial here factors into that.
Oh, okay.
That's the factorization. And then we did a u sub so that the denominator just looked a little bit more like this.
Okay, that makes sense.
And then, yeah. And there's another way you could have done this. I don't know if I want to get, it gets a little more, there's so many kind of subtleties. You could have done something like this also, so that this x + 2 matches. But I mean, let's not even talk about that. That's not necessary. Never mind. I didn't say that. That just is just kind of a clever little trick, but there's enough things going on. So here we just did direct u substitution to make this a u² + 4. And then we did fraction splitting. We did the u² + 4 into u and u² + 4 into the -2.
Can you go over the how you got your answer when you simplified
Here,
the left? Yeah, explain the left part.
the
that
log
left.
part.
Well, like when it's in log, when you haven't combined the like terms, could you just go over that? Yeah, right there.
So how to get to this or how to combine these two?
How you got the final answer, like how you combined it.
Oh, yeah. So there's a rule that says if you have a subtraction of logs, you can turn that into a log of a quotient.
Oh, right.
And then
I see it now.
You see it? Okay, good. All right, let's take a look at another one-off technique, and then we'll get to some strategies that are not one-offs, that are much more procedural steps. You can count the steps if you count steps. Okay, so this is going to be a conjugate strategy. And you know that all those Pythagorean identities, they all have squares, cosecant squared, sine squared plus cosine squared is 1, tan squared plus 1 is secant squared, cosecant squared is cotan squared plus 1. You have those 3 with squares. This has no square in it, and so that's a problem, right? This thing, you can't do anything with it. It's not a Pythagorean theorem type thing. We would love to be able to turn that denominator into one term. Like if it was 1 minus cosine squared, we could turn it into sine squared. If it was 1 minus sine squared, we could turn it into cosine squared. Having the denominator be a single term is very advantageous. And so what we're going to do here, again, is multiply by 1. When in doubt, multiply by 1. So this is a conjugate multiplication problem. So we're just going to multiply by this conjugate and see what happens. So in the denominator, we have 1 minus cosecant squared of theta. And that is going to come from a Pythagorean identity. Now, you may not remember your identity for the cosecants. So if you can't remember it, then you always can go back to your regular Pythagorean, and you can divide by whatever you need to divide by to get cosecant. So cosecant is 1 over sine. So we're going to divide everything by sine squared. Then on the left, you're going to end up with cosecant squared. And on the right, you're going to split the fraction. The sine squared goes into sine squared once, and into the other side, we'll give you cotan squared. All right. So there's the Pythagorean identity that relates cosecant and cotangent. We don't have it quite in the form we want it. We're going to, move the cosecants to the left, move the cotangents to the right. And now we have it in a form that we can replace. Okay. So in the big picture, our denominator is now one term, and that is great because now we could split the fractions if we want. We can do a lot of different things right now. We can change the sines and cosines if we want. Whatever feels like it might work. Sometimes dealing with sines and cosines is just easier because you're more familiar with those. Doesn't really matter. Let's go ahead and split the fraction right now. And maybe we'll convert to sine and cosine. Let's see. So that minus, I'm going to pull all the way to the front. And then 1 divided by cotangent squared, 1 divided by cotan squared is tangent squared. And then over here, I think it's definitely advantageous to switch the sines and cosines here. Because we can't really combine cotan squared and cosecant. Like that's not an obvious kind of thing to combine. So let's go ahead and change those to sines and cosines. So 1 over sine is cosecant. And then we're dividing by cotangent. So that's going to give us sine squared over cosine squared. We can then simplify this a little bit. I'm going to leave a little space here for a second. So I'm going to just cancel out one sine. We have that. Okay. Do we know a function that has a derivative of tan squared? Can we integrate tan squared directly? Or not? We know a function that has tan squared as its derivative.
Yeah, isn't it natural log secant times tangent?
That, not quite. If we were integrating secant, we would have something like that. So right now, what we do know is that the derivative of secant is secant tangent. So that's not going to help us. And we know that the derivative of tangent is secant squared. So we don't have a function that's just going to be an instant antiderivative for secant squared, tangent squared. If we were integrating secant squared, we'd be golden because the integral of secant squared is tangent. So we've got to recognize, and again, this is the hard part about integrating. We have to look at this and be able to recognize that, oh gosh, that has no antiderivative. That means that we're going to have to convert it with a Pythagorean theorem. We know that tan squared can be rewritten. Tangent squared is secant squared minus 1. And now that is good because secant squared is integrable right here. The integral of secant squared is tangent. 1 is integrable. So that is going to be our strategy. If we have a square that's not instantly integrable, then we go to the Pythagorean theorem and rewrite it because then its counterpart will be integrable. Okay, now we're good to go. The integral of secant squared is tangent. The integral of 1 is theta. And then I want to look at this part in detail. Let's not gloss over this. So we integrate term by term. This minus has to distribute to both or to all 3 parts. This integral is very easy with substitution. What do you think we should let u be?
Sine?
Cosine.
Close. Cosine. Why? Let's look at this. Why would cosine work but sine not work? When we take the derivative here, isn't this derivative right there in the numerator? Right, so that's good. We want whatever we let u equal, we want its derivative to match something right in the function. If we let u be sine, then du would be cosine of theta d theta, and we do not have a cosine of theta d theta. These cosines here are in the denominator. So that would not work. So this strategy won't work, but this one will. So this will give us minus tangent theta plus theta. So now we're going to have minus u to the negative 2 du. Oh, I dropped a minus sign. Gotta put my glasses on. This minus sign right here, we're going to move to the front over here. That's going to make this a plus. So sine of theta d theta is minus du. And that minus will come to the front. This is now integrable. And then our final step is to back substitute 1 over cosine, which is secant. And that'll be our final answer.
Can you scroll down?
This way? Or this way?
No, like, yeah, there.
Could you explain how you got tangent squared into secant squared minus 1?
Because our identity says that secant squared of theta is tan squared plus 1. So that's our Pythagorean identity. And so if you subtract 1 from both sides, tan squared is secant squared minus 1.
Okay, that makes sense.
Which, if remembering these identities can be tricky. Here, I think, is a super cool way to remember this identity. If we draw a unit circle, if you take and extend the terminal ray here and drop it down right to there, where that's, the 0.1 comma 0, this is a unit circle, so that side is 1. It will turn out that this vertical side there is going to be tangent and this hypotenuse is secant. This is we'll talk about this triangle later, but it gives you a really nice way to visualize this Pythagorean identity. Tan squared plus 1 is secant squared. And what it shows us is that as this angle starts rotating, you can see that tangent's always going to be this vertical distance. So as theta rotates closer to pi over 2, this triangle gets taller and thinner, and secant will always be the hypotenuse and tangent will always be the height. Gives you kind of a sense for how their values are related. You certainly can see that secant of theta is always bigger than tangent of theta because it's the hypotenuse, that's the bigger side of a triangle. And you can see that when you get to pi over 2, there is no triangle. And so secant and tangent will both be undefined at pi over 2. Because before we get to pi over 2, we're just going to have this tall triangle, and secant and tangent are on the triangle. But as soon as you rotate to pi over 2, you don't have the triangle. So those are undefined. Yeah, but we'll look at that triangle later. But that's just a nice visual way to remember that identity. How else could you do it? You go back to sine squared plus cosine squared equals 1, divide by cosine squared, and you'll get to this.
Okay.
So you could do it either way.
I do like the sine squared minus cosine squared equals 1.
Cosine squared plus sine squared is 1. Yeah, that works well. All right. Last slide in here. All right, so 2 more one-offy things. let's take a look at this first one. This is something that it feels very, I don't know what the right word is. It just feels weird. So we're going to let u be 1 plus root x. And so this turns into u to the half. And if we do our limits of integration, when x is 0, plug it in here, we're going to get u as 1. When x is 1, we're going to get u as 2. But we have a dx. So we need to rewrite the dx. And notice what happens up here. When we do du, we're going to get 1/2 x to the minus 1/2 times dx. Well, this is weird because we're kind of trapped with these x's here. And if we want to solve for dx, dx is going to be 2 square root of x times du. And so when we come over here and we put 2 square root of x du, that's a problem. We can't have x's and u's. It has to all be x or all be u. Can't have a mix. So then we had one earlier today where we said, how can we get rid of that square root of x? And we look at our let statement right here. And if we isolate root x, we'll see that root x is u minus 1. And so what we could do, I'm going to pull out that 2. We're going to have u to the half, and then root x is u minus 1. And that is going to be our strategy. And it feels a little funny that you go back to the let statement and you manipulate it in this way, but just remember that this let statement here, that tells you how many u's you get for an x. And so you can always go back to that statement and you can change it so that you're figuring out how many x's you need for a u, or you can manipulate it so you can figure out how many u's you need for an x. So it tells us how to go back and forth between the two. And if we want to get rid of an x, we just have to go to the let statement and use it. And then this is pretty easy to integrate. So we're going to distribute and we're going to get u to the 3/2 minus u to the 1/2. And then we can use the power rule. And then we're going to substitute in. So plugging in a 2 to 5/2. The 2 in the denominator of this exponent is a square root. So we're going to have the square root of 2 5 times. And square root of 2 5 times is 4 root 2. Minus 2/3 square root of 2 3 times is 2 root 2. And then we subtract off what happens at 1. And we get that.
I have a question. So where you have a u minus 1, you plugged, well, that was from because you plugged in a u into the x and you solved for u, right?
Yeah, we solve for root x.
And
So,
then
right.
where'd you go ahead?
Go ahead. Yep. So we solve for root x, and root x is u plus 1, u minus 1 from right here. And then we plugged it in.
And then where'd you get that 1/2?
This 1/2 here
Oh, on the other one. On
over
the
here.
other. Yep, that one.
So this u right here is being distributed. But this u to the half multiplies to this, and then it multiplies to this.
Okay, I see.
So yeah, the u to the half times 1 gives us u to the half. And u to the half times u gives us u to the 3/2.
Makes sense.
Yeah, cool. And then I'm not going to go through the simplification of this. That's not going to be that important to us. But we could combine these two square root terms. We could get a common denominator between those two, mash them together, and get something little less messy looking. Let's talk about this one, because this one's an oddball one, and there is one in the homework like this. So when you see this, you cannot split that square root, right? Square roots cannot be broken apart when there's a plus or a minus on the inside. They're indivisible. So we cannot split it apart. But what we have seen earlier today, we saw that cosine squared of theta is 1/2. We wrote it the way the identity is originally presented is 1/2 with the 2 in the denominator like this. Doesn't that numerator look a heck of a lot like this?
A lot.
A lot. Right, those things match. So here is the technique we're going to use here. If we multiply both sides by 2, we will have the square root, the part inside the square root exactly. And that is integrable. So we're using this trig identity backwards. Normally, the power reduction identity is used to decrease the power. But here we want to increase the power because if it's a square, we can then take the square root of the square and those will cancel. So now we can make this the square root of 2. And what is the square root of cosine squared?
1 negative 1/2. No, wait.
Not the
cosine.
value, not the value of it, but if we're just going to take the square root of cosine squared, what's going to happen?
Cosine theta.
We are going to get cosine of theta, right? The square root and the square cancel. Is that always true? In other words, is this always true?
Yes.
No. This is only true if x is greater than or equal to 0. If, let's suppose you have -2 and you plug it inside this square root. Well, we know that that's the square root of 4, and this square root symbol means the positive square root. So these numbers are not equal, they are different. The square root of x squared is only x sometimes. Sometimes it's equal to -x. And this brings up a part of pre-calculus that is completely glossed over. You should be writing this every time you take the square root of x squared. The square root of x squared is the absolute value of x, and the absolute value of x is a piecewise defined function that's equal to itself if that's greater than or equal to 0, and it's equal to the opposite of itself if x is negative. So that is the correct way to do the square root of a square. It's usually just sort of blown off in college algebra and pre-calc. So the only reason that this works here is because on this interval 0 to 2 pi, on that interval 0 to 2 pi, excuse me, 0 to pi over 2, isn't cosine positive? If theta is between 0 and 2 pi, do you agree?
Yeah, because
Yes.
cosine's the x values and it's always positive x values.
Yes. So if theta, this little symbol here means, maybe let me not even use that symbol yet. So if theta is somewhere between 0 and 2 pi, cosine's positive, because like you said, cosine is the first coordinate on the unit circle, 0 to pi over 2. I think I said 2 pi again. 0 to pi over 2 is quadrant 1. And in quadrant 1, cosine is positive. So that's why it works. It'll come back to haunt us later, don't worry. So then this is square root of 2, integral of cosine is sine. We're going to go 0 to pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0. Take the difference, and that's our answer. So I'm just going to write something here just because I know at least one of you is thinking this. So if you had this, if you had that, so now we're in quadrant 2 where cosine is negative, the answer here would be that. And then we integrate. And whatever we get here. So sine of pi is 0. And then we're going to have minus a minus, which is plus. Sine of pi over 2 is 1. So just as an example, if cosine is not positive, the square root of cosine squared is going to be negative cosine, not positive cosine.
What if we had limits of integration that spanned both positive and negative cosine?
Yeah, so if you have something like that, then you have to break your integral apart. So just like this piecewise defined function here, if you have a function in here that travels below the x-axis, then you've got to break it apart. Or I shouldn't say it that way. If the function inside here, over here, if it can be both positive and negative when you're dealing with it, then you have to break it into 2 pieces.
So if it were from, say, 0 to 20 pi, would I have to break it into like 10 or 20 pieces?
Yeah, you'd have a bunch of Easter eggs. Yeah.
Fun.
Yeah, you'd have to break it apart. Wherever it's positive, you would do this, and wherever it's negative, you would do that. Yeah.
Thank you.
Not ideal. And almost every time when you look at any of these textbooks, they kind of cook it up for you. And a lot of times you're just doing it and not even noticing it. Like a lot of you just took the square root of cosine squared and didn't think about it. But then every once in a while, they're going to throw one in and you're like, wait, what?
So just be very careful of the domain of the trig function.
Exactly. Yeah, be
Okay.
super careful of the domain. Exactly. All right, man, here we go. Ultraviolet voodoo. You ready for a little voodoo? So this is finally a nice procedural integration technique that has steps. And there it is, right there. And we use this expression. I use it. Not every math teacher will use it, but I like to come up with things that will help us remember formulas. And ultraviolet voodoo it helps us remember the right side of this formula very easily. UV is ultraviolet, integral VDU, this is our voodoo. So UV minus integral of VDU. So a lot of people will, most people have heard of this that have taken Calc 2. Some will not have heard it. If you take it from a pure engineering person, maybe they wouldn't use this cute little way to remember it, but I think it's a pretty easy way to remember this formula. So UV minus the integral of VDU, ultraviolet voodoo. And it's basically what you want to think of it as is a reverse product rule. So it's a reverse product rule. And when we look at this first example, I want you to keep in mind that this is a product. Don't be limited when you're thinking about a product to think, oh, A times B is a product, but A divided by B is not. This is still a product, right? This is A multiplied by 1 over B. So when we talk about integration by parts as a product rule, we're using the word product in a very loose sense. I mean, it's literal, a literal sense, but this is true, right? A times 1 over B, that's a product of A and 1 over B. So just make sure that you're thinking of product in the more general sense, not limited to just multiplication in the proper sense. Okay, so when we do integration by parts, what we are doing is we're starting with this integral over here, and we're going to rewrite it. So the idea is that the integral that we're given, we want to break it apart, and we want to identify part of it that we're going to call u, and part of it that we're going to call dv. So u and dv are given. We have to figure out what they are, but they are part of the integral that we're trying to integrate. So I'm going to always set up this little table. So I'm going to do a u and a dv. So my top row is always going to be exactly what's inside the integral. If I multiply those two together, I'm going to get the integrand. First off, the dx has to be over with the dv every single time. So this is true every single time. And so the idea is that we're going to figure out a u, and then we're going to figure out a du. So that's going to be a derivative. We're going to figure out a dv, and then we're going to figure out a v, and that's going to be integration. So this column is differentiating, this column is integrating. And then we're going to do the u times v minus integral of v du. Okay, so the blue right here, this is what we're given. We're trying to figure this out. And everybody that does integration by parts wants a really prescriptive way to find the u and the dv. For this, there is not really a great prescriptive way. But here's what I will tell you that I think is very good, a very good way to look at this. Two things. So if we have dv, we want to get to v, so we need to integrate. And we have really two choices. We have two functions over here. We could put the x here, and we could put the 1 over square root of x plus 1 here, or vice versa. All right, so we could do either. This one is integrable, right? This is just u to the negative 1/2. Add 1 to the exponent, divide by the new exponent. Or we could swap them. Now, we know that we're integrating to get from here to here. And integrate. And my advice is to pick the biggest part that is integrable. All right, so that's kind of the rule of thumb for dv. Pick the biggest part that's integrable. And rule of thumb over here, we're going to take a derivative. And the rule of thumb over here is a little less, it's a little less solid. In other words, if you can pick the biggest thing that's integrable over here, that almost always works perfectly. Over here, if you can reduce the power of x, that's usually a good thing. That's usually a good thing, but not always. We'll see a couple of exceptions. And so what I mean by that is that if we put the x here, when we differentiate, doesn't the power of x go down to 1? To go from 1 down to 0? Right, now we have no x anymore. We went from x to the 1 to x to the 0. So that's a good thing. If you can reduce the power, you're simplifying. When we get over to this integral right here, that's going to be a checkpoint mentally. We're going to say, oh, is this integral easier than the original integral? And if it's not easier, well, then you made a mistake, because you can't replace an integral with something that's harder to integrate and get anywhere. You need to replace it with something that's easier to integrate. And so this is going to be a real point of analysis right here. And if we can reduce the power of x, that usually is going to make this integral easier. Usually, not always, but usually. So I tend to focus on the DV. If I can pick the gnarliest piece of this integrand that can still be integrated pretty easily, usually that's the best bet. All right, so let's integrate that. And that, let's just come over here to the side. So I'm going to write this as x plus 1 to the minus half dx. And that's just power rule, right? This is just x plus 1 to the positive 1/2. We add 1, and then divide by positive 1/2 means multiply by 2. And then we would do a reverse chain rule if this was not just an x. If that was a 3x, we'd divide by 3. But that's not the case, so we don't have to worry about it. So there is our integral. One thing that you can always do with integration by parts is choose that constant of integration to be 0 every single time. You never have to worry about it. So here, v is going to be 2 times the square root of x plus 1. So now we have all 4 things that you see up here, u, v, du, dv. All 4 things are accounted for down here. So the blue is where we started. We broke apart the integrand into the blue. We differentiated in this column. We integrated in this column. And now we have to fill in. Now we have to do our voodoo. So let's see if we can do the voodoo. So down here, this will be equal to u times v. U times v is this main diagonal here. So u times v is going to be 2x square root x plus 1. There's uv. Minus the integral of v du. So now we're in the bottom row. So now we do this. So it's always the main diagonal minus the bottom row. So 2 square root x plus 1 dx. So there is our ultraviolet voodoo right there. And here is where we ask ourselves, is this easier than original? And if the answer is yes, keep on going. If the answer is no, you go up here and you fiddle with your u and your dv and try another option. So you know that these 2 blue things have to multiply to the inside. If what you chose gave you an integral that was harder than the original, then you just go back and change your u and your dv to something different and try again. But for us, it's easier. So that means we chose properly. And now we just integrate that and we are done. So 2x square root x plus 1. Integral of this, same thing we did over there, power rule. So we're going to have x plus 1 to the 3/2. Divided by 3/2 means multiply by 2/3. And we'll simplify to get our final answer. And that'll be our final answer.
Hey, Jim, so you didn't have a plus C for V because you chose it to be 0? Or
That's right.
V rather? Or
Yeah,
whatever?
that's right. Right up here.
Oh, yeah.
That's
So you
right.
just chose it to be 0, but then we have an indefinite integral as a question, so we give it as an answer indefinitely.
That is exactly right. So the original integral is indefinite, so we will have to have the plus c in the very end. But in this little integration by parts step, you can always choose this intermediate constant to be 0. You could choose it to be another number and it would work out fine. But if you choose it to be 0, it will always work. So that's kind of what we do as a rule of thumb. Because it will always work as a 0, 0 is easier. Let's just choose it to be 0 there. But yeah, what you said is exactly right.
And then so like also for picking U and DV, like you don't always know, and those are always helpful tricks, but it's not always perfect. So like sometimes you just get your hands messy and try stuff.
Exactly.
It doesn't work, you go back. It doesn't work, you go back, and then it does work or something.
And that's right. And usually there's only 2 or 3 choices. Like when we look here, we have this function and we have this function. So we can put one with U, one with DV, and if that didn't work, we just swap them. So let's check out this one. So here's another one. And I picked this one because it has a couple of interesting features. So if we look at the U and the DV, I'm going to draw this little table the same every time. And the DX I know has to come here. So when we look over here, there's really two choices, right? There's an ln x, there's an x squared, and you know how to differentiate ln x. So that seems like, okay, I could put it there. But what about if we put it over here? If we put it over here, can you integrate natural log? Do we know how to integrate that yet?
It's 1/x.
That's how you differentiate it.
We don't know how to integrate that yet,
Ex-
right?
Exactly. We don't know how to integrate that yet. So this is one of those ones where you say, oh gosh, natural log of x can't even go there. It has to go there. And that means that we'll put the x squared over there. All right, so we know how to differentiate natural log of x, but we do not know the integral of natural log of x yet.
Did we learn that this semester?
We're going to learn it next week.
Oh, okay, perfect.
Yeah, it's a good one.
Perfect timing.
It's going to be a good one too. It's a fun one. This technique of integration by parts allows us to integrate a whole bunch of functions. So we're actually going to integrate natural log of x with integration by parts. We're going to integrate inverse sine, inverse cosine, inverse tangent. There's a whole ton of functions we can integrate with this technique. So now let's fill in our little recipe here. This is going to be our recipe for our voodoo. So we're going to find du by differentiating. We're going to find v by integrating and choosing the integration constant to be 0. So that is our voodoo recipe. And now we just have to plug it into our voodoo formula.
Wait, sorry, how did you say we're finding V?
Say that once again.
How are we finding V?
So v is found by integrating. So if you have dv equals dx, the way you turn dv into v is by integrating. And then we integrate on the right side here, and the integral of x squared is x cubed over 3.
Got it.
And then in this column, we differentiate. So the left column is always derivative, the right column is always integrate.
And when you do that operation of the integral, it cancels out that dx, or?
Yes, because the integral, so if we have this expression right here, and we integrate both sides,
They like cancel each other. or-
exactly. The integral symbol and the derivative symbol cancel each other. And then over here, normally we would write x cubed over 3 plus c. But again, for the purposes of integration by parts, we can always choose this to be 0. So now we do our ultraviolet voodoo. So we do the main diagonal multiplication. So that's going to be x cubed over 3 multiplied by natural log of x minus, and now we do the bottom row. So it's always going to be that pattern. I'll always write this integration by parts table the same way every single time. So now the bottom row, we're multiplying. So it's the integral. So it's uv minus integral of v du. And when we multiply those two together, we have x cubed over 3 multiplied by 1 over x dx. Well, that simplifies. We cancel out an x. We can pull out the 1/3, and that's just going to be an x squared dx. And that is where we analyze. We say, oh gosh, do we pick the right thing? Is this easier than the original? And the answer, of course, is yes, because we know the antiderivative for that. So then we can cut to the chase here. We can write our final answer. And here we do have a plus c. Right. Do another one unless you have a question on that. So the integration by parts, it really, oh, we're gonna do it right now. I kind of, in my morning class, we didn't get as far, so we didn't get to do this because we were talking about their test. So we didn't get this far. All right, so ultraviolet voodoo, UV minus integral of V to U. And you're looking here, and I know what you're saying. You're saying there's no product. You said it was a reverse product rule. That's one of the coolest things about this technique is that we can use it. We can think of that as inverse sine of x times 1. So let's set up our table. So this is what we're trying to fill in right there. Do you see that I cannot put inverse sine right here? If we put inverse sine right there, then we're asking the question that we're trying to solve, right? To get to V, you would have to integrate this, and we don't know how to integrate it. So doesn't the inverse sine have to go over here? We know how to differentiate it. And we're just going to put the 1 there. And then we integrate over here and we get the V is X, and we differentiate over here. So we get the du is dx over the square root of 1 minus x squared, the derivative of inverse sine. And let's see if it works. So now we're going to do our voodoo. So we do UV. So this is the main diagonal, UV minus integral of the bottom row, V to U, the bottom row. So we're always going to do this main diagonal minus the bottom row. And this is where our moment of truth is. We say, is this integral easier? And the answer is a resounding yes, because what integration technique can be used for that integral?
U sub.
U sub, because the inside of the root is a quadratic. And when we differentiate that quadratic, we are going to get this linear numerator. So let's come off to the side, and we're going to use a U, not the same U, not the voodoo U. So we're going to let U be 1 minus x squared. Du will be minus 2x dx. And let's go ahead and isolate x dx. And then we have a perfect U sub. So we'll have this x inverse sine x minus, all right, so the x dx becomes du over -2. So I'm going to put 1 over -2 in front. And then inside, we're going to have u to the -1/2 du. Make sure that you agree with that. So the x dx, that's becoming du divided by -2. And we have 1 over the square root of u. 1 over the square root of u, we're going to pop it up to the top and make the exponent negative. And now we can fly to the end, fly to the finish line. That's going to be plus 1/2. I'm going to leave a little space here. We add 1 to the exponent. We divide by the new exponent. And then we're going to back substitute. And that will be our antiderivative for inverse sine, not something that anyone ever remembers.
Do
So
you
is
do
this-
anything? Oh,
Sorry, go ahead, brother.
you first?
I was just asking if this is like another thing to do now on top of U substitutions, like we're just adding a new tool, basically.
100%. So this strategy, integration by parts, is equivalent to U sub. It's like a super formal integration technique. A lot of those other integration techniques are kind of that we did earlier today are just kind of in for special cases. And this is a much more sort of bona fide integration technique.
And then would it be advantageous to like use a different variable instead of U when doing U sub so we don't confuse our U's?
Well, once we actually, after we did the voodoo, there's no more U's in here, right? So we did our voodoo with the U up here and the V and the DV, and then we end up with this expression that has no more U in it. So if you can draw a V that doesn't look like a U, you could use a V if you wanted, or a W, I guess, because we already did use a V too. Most of the time it doesn't matter though, because your U is just temporarily there once you do the UV minus V to U.
I'm just thinking like converting limits of integration. I might glance up my page to find
Yeah.
the U equals this. Or I guess if you keep it in the table, then that would
Yeah,
help.
you'll have to see what works and see if you end up with something that, you know, if you end up finding a snag, then definitely use a different letter. I haven't found that I usually need to though. All right, let's do one more. Let's check this one out. Dustin was asking about it. Let's do it. So here's another one where we have no choice. It's natural log of X times 1. So there's really only one function in there. And we can't put it with the DV because we don't know how to integrate it. And this is done, the right column is integration. We do know how to differentiate it though. That's 1 over X dx. And then check this out. This is so clever. So the integral will be UV. So that's the main diagonal. There's UV minus the integral. And what is V times du?
Isn't that just 1?
Yeah. So we end up with this. Those x's cancel, and here is the antiderivative that you've been waiting to see for so long. Ever since you learned how to differentiate natural log, you wanted to know, well, what's its integral? If I know how to differentiate it, what's its antiderivative? There it is. So that function right there is the antiderivative for natural log of X. If you differentiate this, you will get back to natural log of X. Let's confirm. Let's just confirm. So let's suppose we have x ln x minus x plus 5. Take the derivative. So for this part, we need a product rule. So we do first times derivative second plus derivative first times second. The derivative of negative x is -1. The derivative of 5 is 0. Let's see what we get here. 1 plus ln x minus 1. Sure enough, we get back to ln x. So this integration by parts technique, although we really do think of it as a reverse product rule, we can think of it also as being a more general strategy that's going to help us with some of our pretty unique functions. The inverse trig functions, the natural log function, integration by parts will be able to unravel and find those antiderivatives, which is kind of cool. All right, folks, you ready for a weekend?
I'm ready to do some of the homework.
Ready for homework? That's what I want to hear. It's so miserable out. It's perfect math homework time. All right, well, I will be checking our little question board here. If you're doing stuff over the weekend and you're stuck, write something in here and I will get back to you, or you can do the ask my instructor thing or whatever, and I will get back to you.
I have a quick question.
Yeah, go for it.
Could you go back to the example with the inverse sine?
Mm-hmm.
Where did the 2 come from like 1/2 times 2 times u to the 1/2?
This comes from, so this 1/2 out in front, right, that is this. And then when we integrate here, we add 1 to the exponent and divide by the new exponent. So when we add 1 to -1/2, we get +1/2 divided by 1/2. And that's what this is. When you divide by 1/2, it's equivalent to multiplying by 2. Are you agreeing with me?
Yeah, that makes sense.
So if we, yeah, so if we're integrating u to the u to the -1/2, that's going to be u to the +1/2 divided by 1/2. And then those 2's will cancel. Any other questions anyone has?
You're probably gonna get some more questions when I do the homework, but yeah, I think we're good here.
Totally fine, man. Post in the question board, do the Ask My Instructor, and all good. All right, well, I will see you all on Monday in person. There will not be a snowstorm on Monday.
It's Colorado, we never know.
We never know. You would think 4 inches of snow would not hold us back from getting to campus, but all good. At least we have this as an option, and you're not like 2.5 hours of math behind.
Yeah, especially with this class, you have to be on your toes.
I know, it's definitely agreed. All right, well, I'm going to stop the recording.